Hi, I'm Dr. Leonie. Welcome to Basics Physics. This is week 5 and this is 10th of November 2020, chapter 4, and the title is Force and Motion. You're going to do the same preparation before you start the class. That is 4 pieces of A4 paper, and then you're going to stapler top left of these papers. The first paper, you're going to have a center line to separate it, and then the left column is Q1, referring to question 1. Come with the statement object is it kinematics one direction or two dimensions? And then you have your name on top, program and student ID, and DIY question number 1. Then for the question number 2, it's quite similar. And then question number 3 is a bit extra columns here. So now you have 3 columns. The first one is the question from the slides later, and the second one is the DIY question 3 from yourself, and the third one is you're going to get the question from your friend Q3. And after you got your question, you're going to write your friend's name, and then you're going to ask her what does she like, what kind of food. Question number 4, same. So you're going to ask your friend Q4 what is his or her favorite movie. Are you ready? So after you have all those 4 papers completed, you have answered the questions, you also DIY your question yourself, you also collect from your friends and then you solve it, collect from friends and solve it. You're going to stapler it and then submit. This is taken from last week kinematics chapter 3, when we're interested at the object, one object here, and we don't care about who is pushing it or who is stopping it or who is punching it. We don't care about that. We just want to know what is the motion, the position, displacement, velocity, acceleration of the object. We say that we are studying this object under the kinematics. For our case, we're interested at the one direction, and sometimes two dimensions. For the 2 dimensions is a bit complicated, but if we manage to dissolve the force, we manage to solve the motion into x component and y component, then it'll be easier. For chapter 4, we are studying something about the force and the motion. Sometimes people will call it kinematics in actions, or we call it dynamics. We're going to cover Newton's first law, Newton's second law, Newton's third law, some of the applications, tensions and frictions. Chapter 2, 3 and 4, when we need to categorize it under which section of the physics, it falls under here, classical mechanics. Why we say so? Because of the 2 reasons. The first one, because our object is moving not so fast enough. What's so-called fast? Fast is as fast as the speed of light. How fast is speed of light? 1 second, it can circle the earth for close to 7 times. Circle the earth. This is the earth. 7 times. 1 second, not like 1 hour, 1 second. Why we our study is fall under classical mechanics? Because is the size of our object is relatively big. It's not as small as the molecule or as small as the atom or the electron, but it seems quite big. So that's the reason our chapter 2, 3 and 4, it falls under the classical mechanics. So for this week, we are interested to know what is uh, uh, the formula that can redefine our motion. Force. Force is the thing that causing the change of our object motion. So when we define the force, we can say that a thing that can change the other object motion or the shape, the form. But for our case, we are more interested in the motion of the object. Force can be categorized into two big groups. The first one is the contact forces. When there are two objects and they contact each other, then we say that it's under the contact forces. It included the friction force, the tension force, if we are pulling those two together, and the normal force. There's a kind of force opposite to the gravity force, the tension force, the normal force. Air resistance force, when it's moving so fast and there's air molecule going to block it. Applied force is when somebody like Incredible Hulk is pushing the mouse. So we say there's applied force. And the spring force, if there's a spring. While action at a distant force means that those two objects are not contact each other. It's included the gravity force, the electrical force, and the magnetic force. For this week, we're interested at these forces: the frictional force, the tension force, the normal force, the applied force, and also the gravitational force. The other forces, no, at the moment. The first one, the friction force. When there are two objects that touching together at the surface there will be a kind of the hidden force that making the object, one of the object, move slow. And it depends on the two factors. The first factor is what is the friction coefficient, and then what is the normal force applied to the surface of it. The friction coefficient, when the surface is very smooth, it means that we're going to have a small value of our this coefficient. When our surface is very coarse, it's very kasar, something like that, then our value is very big, the coefficient. Another factor is what is the normal force applied to it. It means that when the object is very heavy, it's very dense, then our N will become very big. It means that later on our F will become a very high value here. Or to say that if the object is very light, like a piece of paper, it's very light, so our N will be very small. So there will be a very small friction force apply this paper to the surface there. Tension force happens when there are two objects connected with a cable or a rope there. So the tension force is the force inside the rope, the cable. Later on, we're going to have one example to calculate what is the tension force inside the rope. The normal force is the force that perpendicular to the surface, 90 degrees to the surface. When we have the object, a block here, is on the horizontal, then the normal force, it is 90 degree on top of the surface there. So it is the opposite of the gravity force. But for the case that we have the object is on top of the inclined slope there, this is the gravity force. So what is the normal force? The normal force is the force that is perpendicular to the surface, 90 degrees to the surface. So I'm going to use the blue color to identify it. So the normal force is, this is the normal force. See, that's the difference. It's not always opposite to the gravity force. It depends on the surface. 90 degrees to the surface. 90 degrees to the surface. Next one, gravity force. Gravity force is the force considered as action in the distance. It's not contact with the object. So the general formula is W equals to mg, or sometimes we write equals to Fg, the force because of the gravity. The interaction between force and object is well described by Newton's law of motion by Sir Isaac Newton very many years ago inside his book. So the book was written 1687. That's around like 300 plus year, 300 plus year, so many years ago. But the formula still be usable. What is the first Newton law? The first Newton law says that an object that's at rest, it always at rest. This object is resting. After we observe it for 20 seconds, it's still at rest. But if this object is moving, after 20 seconds, we see that it's still moving. This is what described under the Newton's first law of motion. Newton's second law of motion is to make it into a calculatable condition. Means that if you want to know what is the force making the rubber, this one, to move just now, we can use the formula here. F equals to ma. What is the force? What's the force that applied to the rubber to make it move? And m is the weight of the rubber, and a is what is the acceleration of the rubber. Is it moving faster and faster, or is it moving at a constant speed? If we know what is the weight of the rubber, and we know what is the acceleration of the rubber is moving, we can calculate what is the total force that apply to the rubber here. Newton's third law says that when there is an object apply a force on the second body, knee apply force, the second body simultaneously will apply a force the same magnitude, the same value, and the opposite direction on the first body. When I push the rubber here, eraser here, I can feel my finger like going to the opposite side there. Even though I'm pushing it, but there's opposite force that I can feel. Now your task, before that, there's a movie that could well describe these three forces. It's called The Gravity, 2013. The movie act by Sandra and George Clooney. Newton's first law says that if Sandra detached from the spaceship, she's going to move at the same direction and same speed and will not stop. Yes, when we watch the movie, we see that Sandra is moving further away from the earth there and non-stop. The direction the same, the spinning speed is the same, the magnitude of the velocity is the same. But if she intends to save herself and go back to the earth there, what can she do? She can think about the Newton's third law of motion. Means that if she's going to apply then the so-called the opposite force far from the outer space, then she'll make herself moving quite close to the Earth atmosphere there. What can she do? She can apply the fire extinguisher to this direction, to the left hand side, and then what will make her move to the right hand side? Yes, what described inside the Newton's third law. There is an opposite, same magnitude, but different direction force applied to her. This can save her. How about for the F equals to ma? What can we apply in her story here? If she using the fire extinguisher, we can calculate what is the force pushing her back to the Earth there. How? F equals to ma. So the easy one is the m. M is the total weight, Sandra, the astronaut, and the fire extinguisher. Let's say total is 68 kilogram. A, if we know what is the acceleration that making Sandra moving back to the Earth here, what is her acceleration? Let's say the acceleration is 20 meters a second. Then we can know what is the force that pushing out from the fire extinguisher. What is the force? So for a case, we can know all these three laws. These are two of another example, one happening on the Earth here, and one happening from the Earth to the Moon there. Okay, for the rocket, it's more obvious reflecting the third law. The first, the rocket, we're going to expel out a lot of the gases and the heat, and it's going to create the so-called opposite force, making it move away from the Earth. So for Q1, what you need to do, the first one, you need to copy this one. And then the second one, you're going to translate into Bahasa Melayu, and then you're going to draw one image to represent each of the force here. So when we translate into Bahasa Melayu is hukum gerakan Newton pertama. Satu objek yang statik akan kekal statik sehingga satu daya luar yang dikenakan kepadanya. Okay, let's move to the next slide. Example 4.1, you no need to copy it, you just go through on a piece of blank paper, you no need to submit. Okay, the first question is, two applied force are acting on a block, and find the acceleration of the object. You see, you have 20 Newton applied to the right hand side and then 10 Newton to the left hand side. Guess, will the block move to left hand side or right hand side? Yes, right hand side. Why? Because there's more force, a higher force at the end. So when you want to know what is the acceleration, do we have the m? Yes, we have the m, it's 5 kg. Do we have the a? No, we don't have the a. Do we have the force, the final, the clean force, the net force? Yes, it is 20 Newton minus 10 Newton. So at the end, we're going to get the value of the a equals to 2 ms minus 2. For the second case, we just realized that, oh no, there is a friction force of 2 Newton. Now, what is the new acceleration? When there's a friction force, we are guessing that the block will move slower than before. It will be a smaller value than 2 ms minus 2. So for this case, our net force, we want to consider the friction force. Sorry, should be 5 kg here. 5 kg times the a, we don't know. So we look at the net force is now equals to 8. So we get the 8 equals to 1.6 times ms minus 2. When we compare those two, we realize that it becomes slower. Why? Because of the friction. Go to the second example. There are two objects are tied on the floor and being dragged by a horizontal force. We don't know the force, how much. Determine the force acting on the objects and tension force T. We want to know two things. The first one, what is the force here? And second one, what is the tension force here? To find the force, the first one, so we use the general formula, F equals to ma. What is A? Oh, luckily we are given the A. A equals to 4. How about the M? So we have two objects. So the M is 150 kilogram plus 50 kilogram. So at the end, will become F equals to 800 Newton. The next question is, we want to know what is the tension applied to the rope here. When we ask the rope, if the rope can answer us, rope, who are you pulling? Are you pulling 50 kilogram? Or you are pulling 150 kilogram? Or you are pulling both? Then the rope will say, I'm just pulling the 150 kilogram. So since the rope is pulling 150 kilogram, so the tension force equals to m2 times the acceleration. Is it the same as 4? Yes. So now we have A equals to 4. How about m2? 150. 600 Newton. There's 600 Newton tension applied to the rope. So we need to have a very strong rope so that it won't snap off. Let's go to the example 4.3. A force F equals to 20 Newton is applied to an object of 4 kg mass at angle 60 degree with a horizontal, and there is a friction force 2 Newton. We want to find the acceleration of the object. For this case, we are doing the two-dimensional because there's angle inside our problem here. A. We want to find the acceleration of the object. We need to ask the first question. We want to find acceleration horizontally or vertically or 60 degree. The answer is we want the horizontal acceleration. So we want to find what is the horizontal acceleration. To find the horizontal acceleration, we need to dissolve the Newton into horizontal Newton. So at the moment, the friction, yes, is already horizontal. We want to dissolve this one. So how to dissolve? We use the cos and sine. So for this case, we're going to use the cos. The F horizontally equals to cos 60 degree times 20 Newton. So we get 10 Newton. F horizontal is 10 Newton. But we need to include the friction force. So the net force horizontal equals to 10 Newton minus 2 Newton equals to 8 Newton. And it also equals to MA. What's the M? 4 kg. What's the A? We don't know. So 8 Newton. So at the end, A is 2 meters a second. Done. B, if the force F is stopped when the object has gained a velocity of 5 meters a second, how far can the object move? For this case, the block is pushed, and then I push it, and then there's a line, and I stop pushing it, and see that, oh, the block is still moving, and we say that this is the starting velocity of the block. And because of the friction, the block is going to stop. You want to find what is the distance, and then the initial velocity is 2 meters a second. Since the question B, we doesn't have any extra force there, means that later on we're going to use the kinematic formula to find it. So what formula can we use? We can use this one. Do we have the V? Yes. Do we have the U? Yes. Do we have 2? Yes. A? Yes. S? We don't have. So we can get the S equals to 6.25 meter. Means that after we stop pushing, the block going to move for extra 6.25 meter, and then it stops. Question number 2. There's a block 10 kg on a rough horizontal plane and is pulled by a horizontal force. If the coefficient of static friction between the block is 0.4, find the normal reaction force, the static reaction force, and the minimum force required to move the block with a constant speed. So let us put into a diagram first. The block horizontally pulled by a horizontal force, the F here. A, we want to find what is the normal reaction force. A normal reaction force equals to opposite. For this case, we can say it is direct opposite of the gravitational force. So equals to m times g. We need to put minus because later on going to serve us as a positive value here. M is 10, g is 9.81, minus. So our normal force is 98.1 Newton. Get it. B, what is the static friction force? B, static friction force. Friction force equals to the coefficient of the friction times the normal force. Do we have the coefficient? Yes, 0.4. What is the Newton force? What is the normal force? 98.1. So we're going to get the value there. 39.24 Newton. It's good to have the negative because it's moving to the left hand side. C, the minimum force required to move the block with a constant speed. So to move the block is to against the friction. How much the friction? The friction is 39.24. So the net force to move the block equals to the applied force, that is the F, minus the friction force. It's also equals to MA. So now we want to put one by one. Do we have the F? No, we don't have the F. Minus the friction force, 39.24. equals to ma. M, what is the m? M is the weight, it's 10 kg. What is the a? A depends on the question. The question says that the constant speed means that let's say the final speed is 5 meters a second. The initial speed is 5 meters a second. So 5 minus 5 equals to 0 divided by t. Means that a equals to 0. F minus 39.24 equals to m times 0 equals to 0. So F equals to 39.24 Newton. Means that in order to move this block, we need to have somebody that saying, oh, I'm going to contribute 39.24 Newton to the right hand side. At the end, the block going to move but at a constant speed. Let's go to the Q3. Oh, before Q3, remember to DIY Q2. Okay. You can change the story, you can change the number, and then you solve it. Q3, when we look at the question there is a 30-degree angle here. So when we put it into a diagram, it's like this. We have a block. A lecturer is pulling it at 2000 Newton. And then there's a friction coefficient 0.3 at the angle 30 degree. So A, we want to find the normal force. The normal force is the perpendicular to the surface force here. When we draw it, to check all the forces applied to it, we see that there are two forces. The first one is the gravitational force. M is 200 and then G is 9.81. So we're going to get negative 1962 Newton. But because of the normal force is 90 degree to the surface here, if we can dissolve it and to find what is the so-called opposite force to this green line here, then we can find what is the normal force. So to find what is the green line, is equals to cos 30 times 1962 equals to 1699 Newton. Okay, we solve for this one. B, the net force. We need to ask the question. The net force, we're interested at which angle, which component. Is it vertically or horizontally or the 30 degree? Yes, the answer is the 30 degree. Interested. So we want to find the net force. In order to find the net force, we need to dissolve the gravity force into the opposite of the inclined slope there. So I use the purple color. The gravity force causing some of the force to the 30 degree here. So to find this one, so we'll use 1962 times sine 30. You get negative 981. So we have negative 981 there. To find the total force equals to the force to the up there 2000 Newton minus the force by the gravity. Also, we need to minus one friction coefficient force here. How to find the force there is using the formula mu times the n. So mu how much? 0.3. How about the n? N equals to 1699. So at the end, when we calculate all together, we're going to get the net force is 509.3 Newton. Where is it? So I use the blue color here. 509.3, the net force. Why from 2000 Newton become 509? Because of the naughty friction force and also the unseen gravity force pulling down. Next one, C. You want to find what is the acceleration of the block. Then it will be easy task now. To find the acceleration, F equals to ma. Which F? This F. 509.3. Which A? Don't know. How about which M? Yes, 200. So can we find the A? Yes, we can find the A is equals to 2.55. And the last question, D. The time taken for the block to travel 30 meters from rest. So since it's already stated, the rest is rest. Do we have the V? No, we don't have the V. Do we have the S, the distance? Yes, 30 meter. Do we have the time? No, we don't have the time yet, but we want to find the time. How about do we have the A? Yes, we have the A. How much? 2.55. Which formula that we can use? The formula you can use is S equals to UT plus half AT squared. Well, so one we plug one by one. S is 30, U is 0, T is we don't know. Half, what is A? 2.55. What is T? We don't know. So we can find the value of the T. So the T will be 4.8 seconds. Means that using the 2000 Newton force, after 4.8 seconds, we're going to make this block move for how far? Yes, 30 meters. How far is 30 meters? That's roughly you're running 30 of your step there, 30 meters. Okay, this is the big version of solving the problem. Q3, so later on you DIY yourself. And then after that, you go and search who is your Q3 friend. And then you copy the question. And then you solve. Okay. Remember, your friend's favorite food, you need to ask her later on. For the Q4, this is the problem. I won't discuss its details here. So later on, you want to find what is the acceleration if the friction is neglected. You don't want to care about the friction. And what is the acceleration if the friction is 45 Newton? So DIY yourself and then find your friend Q4, copy, and you solve. Okay, after you have completed all the things from paper, first paper to the second, third, and fourth, you're going to stapler it, and then you snap a photo, submit by 12th of November, Thursday, before 10 o'clock. Where should you do the submission? You go to this website, tinyurl.com/EFT1103 week 5, and then you submit, do the submission. This will consider as your attendance also. If you have anything, then you can email to me. This is my email address. Okay, that's all. Thank you. So for next week, that is the semester break, and I'm going to see you again on 24th of November, Tuesday. And on that week, we're going to have a quiz, a short quiz. Okay, bye.